We'll get started. I hope you're all able to see me and also hear my voice. Can I just get a quick voice response from someone, please, that they're able to see me, hear my voice, and also see my screen?
Yes, Professor.
Great. Thank you, Shahad. Appreciate it. Yeah. So I'm going to, today's lecture will be online as you're already joining. Before we begin, I just want to point you to a couple of things. First of all, I have posted the quiz one study sheet here. You should be able to see it on Canvas and start getting ready for it. Briefly, it's going to be on February 26th in the evening, okay, 8 p.m. to 9:40 p.m. That's actually 9:30 p.m. plus 10 minutes to scan and upload your work. This is Atlanta time. So if you're in the Pacific Coast, West Coast, you should be starting your work at 5 p.m. Pacific time and ending at 6:40 p.m. Pacific time. Europeans, because they are 6 hours ahead of time, I have to prepare probably a separate exam and also have an earlier start time. Most of them will be starting their time, 8 p.m. European time, and ending their time, 9:40 p.m. European time, except one exception. Also, please note that you have to upload it as a PDF file. You could do it with a piece of paper, scan it, and then upload it. Or you can use a tablet, write it, save it as a PDF file, and upload it. Please give plenty of time for scanning and uploading it because a lot of people will be using Canvas towards the last 10 minutes. If you miss the deadline, you will lose a lot of points. Because do not email me the submission, because then I have to upload it back to the Canvas, and all the grading is done inside Canvas. Points are posted inside Canvas. So you need to be managing your time properly, have a good access to reliable internet, have your iPhone perhaps as a backup. You could use it as a secondary source of internet. All of you know how to do it. And if anybody emails to me, I will accept it, but there'll be a 20% penalty. But when I say late submission, I'm talking about within 5 to 10 minutes, not a day late, okay? It's open book, open notes, but you do treat it like a closed book, closed notes. Create a study sheet, take notes, have everything ready, because it's hard to scroll through my entire notes, maybe even review videos and so forth. You need to come prepared just as though it's a regular class exam where the professor allows you a few pages of cheat sheet. And also, please do not use AI tools because they are prohibited in my work. Okay. Honor code applies, obviously. I won't be in your dorm or your house or your apartment, so you have to work independently. Any collaboration, any sharing information, immediately will get a failing grade. And also, you will be asked to basically leave the class. Okay. You can use scientific calculators, it's fine. But there may be some calculus, integrals, differentiation. Do not use a calculator or computer tools to do those things because you are expected to explain what you're doing. And so use the calculators only for numerical calculations, also sine and cosine, trigonometry type of a thing. There'll also be concepts you need to be familiar with. Here is a laundry list of concepts. You can start looking them all up, understand, review my notes, review the video, make sure you have a clear understanding of it. I may have something like a 20 to 30% devoted to concepts. Rest of them would be either analytical problems or numerical problems. These analytical and numerical problems would be similar to homework 1 was really a X-file. So we won't be running a lot of computer programs, although you may be able to check some solutions with computers. But in general, it'll be of this nature. 1, 2, 3, there are some analytical numerical problems. But throughout my Canvas site, I have practice problems, worked out examples. I ask you, show that, prove that, verify that. So you should be able to look at all of those things. Okay. And it starts from the very beginning on the very first day of our class, which is the January 12th, I believe. And it's going to conclude with the 3D incompressible flow over lifting bodies module. Okay. So we are still not there yet. So we are probably going another week or so. Most likely next Wednesday, I may be reaching an endpoint like the 18th. I'll tell you, this is where the quiz ends. Clearly mark it for you. So please practice everything. Review all the exercises, not just the ones that are posted explicitly, but some of them are embedded inside the PowerPoint and PDF. And please be familiar with it, okay? So this is the study sheet. So you have plenty of time to prepare for it, but I just want to give you an idea what's going to be in the exam and go from there. Now, we can take more questions on the study sheet when we are meeting together in the classroom. If you do have some questions, you can ask me at the end of this lecture, and I'll try to answer them, and those would also be recorded. But let me go to the module section and tell you, where we are in the class. Okay. These are all earlier topics. We have done 2D building blocks. We have done the assignment number 2, thin airfoil theory. On Monday, we did the panel methods here, last week. And Monday, we did the 3D incompressible potential flow. We showed you how to compute the flow over a sphere. Now, I'm going to cover this problem, this topic, because homework number 3 builds on it. Okay. So today I will complete it as far as I could go, but there are some practice problems here. There's a worked out example inside the PPT. So you should be able to get started on the homework number 3. Then I'll also show you how to check your answers with the MATLAB code. Okay, do by hand, then check your answers. Okay, so that's what we would cover. Earlier, I thought we would first cover some of the theorems that are important for this topic, but we are going to defer the theorems till Monday so that you can get started on the homework number 3, because it's due less than 10 days from now. It's not this weekend, but the next weekend, right? So I have already downloaded this material, so I'm going to get started with this. Are there any questions on this material so far? Everyone okay with it so far? Great, thank you. All right, so let me get to the PowerPoint slides. I'll go to the full screen mode here. And is everyone able to see my PowerPoint full screen mode, finite wing theory lecture notes? Great, thank you very much. Yeah. So what are we going to study in this one? If you have a textbook, Anderson, which is an undergraduate book, you're not required to buy it, but we use it in our undergraduate classes. They have a chapter 4 that's related to thin airfoil theory. Of course, we have reviewed thin airfoil theory as part of our class lecture almost 10 days ago. And we derived some important expressions like CL is 2 pi times alpha minus alpha naught. And I showed you how to compute the CL and also pitching moment at the quarter chord. If somebody gives you a quarter chord line shape, analytical shape, and also the angle of attack. And we said more accurate solutions can be obtained using panel methods or, of course, using CFD. Okay. Panel methods is used in X-File. You already practiced it, X-File work. CFD, we won't have time to practice it in our class, unfortunately. But we have a graduate course on CFD where they talk about a lot of the theory behind it. So let's quickly review what does the two-dimensional theory gives us. Okay. Basically, it comes up with the thin airfoil theory comes up with this dotted line for a lift versus alpha, where it crosses the x-axis, where the lift coefficient goes to 0, is called a zero lift angle of attack. Alpha when lift is 0. So the slope is 2 pi when alpha is expressed in terms of radians. Of course, in the real world, because of the stall, the lifter stalls here, and also it stalls on the negative angle of attack. If you keep pitching an aerofoil up, it's going to separate on the top surface and stall on the top surface. If you keep pitching it downwards, it's going to stall on the bottom surface. So the black curve may have a slightly different slope. So in our lecture in this class, we are going to call this A naught. Okay, A naught may be slightly lower than 2 pi. So if in an assignment or in a problem set or in an exam or in your industry practice, if this slope is available from experimental data, that's what we would use. But in the absence of experimental data, we will assume that the slope of the lift versus alpha in 2 dimensions is 2 pi. Same way, pitching moment may be computed by our thin aerofoil theory, also by our panel method. But in the absence of viscosity, we are going to get more or less a constant value about the quarter chord point, okay? Pitching moment about the quarter chord point. Again, the black line represents the stall, the moment stall, moment stall. So moment stall means as you pitch up, you get a lot of separated flow. So sometimes you get a vortex that flows over the aerofoil near the trailing edge. Anytime where you have any vortex, you get a very, very high velocity. From Bernoulli, you get a low pressure. So the bottom surface of the aerofoil lifts up the tail back end of the aerofoil, producing a large nose down pitching moment. So that's what this is happening. Very large nose down pitching moment. This is called a moment stall. This is called a lift stall. I hope you're able to see my mouse being moving. So let me change my pointer to a laser pointer. Okay, so this is the lift stall. This is the moment stall. Our thin aerofoil theory or a pure panel method will not give us drag. So if you want a drag, you have to go to boundary layer theory, some way of telling where is the laminar flow, where is the turbulent flow. We need to have some way of telling where the flow is separating. All those information should be known. Then you have to either numerically integrate the boundary layer equations, which are PDEs, or some integral form of the boundary layer equations. I promised to tell you how X-foil does the boundary layer. Again, I have to defer that. Maybe I'll just post it as a module for information purposes. Because our course is primarily focused on inviscid flow, I do not want to go sidetrack to different venues, and we may lose track of where we are. Okay. But anyways, there's a minimum drag value. By the way, we came up with a very important concept called the drag count. Drag count is 0.0001. So it's the 4th significant digit. That 1 is called the drag count. So when we plot this curve, it's very important to scale the vertical axis so that we can resolve the drag variation from aerofoil A to aerofoil B. Otherwise, we are going to be in bad shape. We won't know what's going on because they will all look the same in this plot. So this is not given by our theory, inviscid theories at all. You need a boundary layer behavior. Why does the drag shoot up here? Because of the stall. Same way, it is because of the lower surface stall. Sometimes you'll get a bucket-like shape. We call it a laminar drag bucket because the drag is a laminar, mostly laminar flow. Then suddenly, the drag jumps up. Okay, so that's called a laminar drag bucket. How does the experiment do? This is an aerofoil called FX aerofoil. You could see that there are 2 curves. This is for the lower Reynolds number. This is for the higher Reynolds number. CD is shown in the horizontal axis. Notice they multiply by 10 to the power 4. So this is 110 times 10 to the power 4, 120 times 10 to the power 4 minus 4, and so forth. So drag, lower Reynolds number, higher Reynolds number, CL versus alpha. This aerofoil is mostly a laminar aerofoil. There's a large region of very, very low drag, then it shoots up. Okay. So this was a very famous aerofoil that was used in Navy, military, seaplanes, and all kind of stuff. It's an FX type of an aerofoil. Okay. All right. Now we go to three-dimensional wings. So Wright brothers had already flown their airplane in 1903. They had no knowledge of drag. They didn't knew that they need some kind of a propeller to push the airplane forward. So they had a piston engine, very, very small powered piston engine, turning a two-bladed rotor to pull the vehicle forward. It's what you call a tractor propeller, the front of the aircraft. And then they were propelling it forward. If you don't have a propulsive means, becomes a glider. Then you are at the mercy of the gravity. Okay, you use the gravity itself to propel you forward. So three-dimensionally, when people started flying these things, they found the lift curves was not 2 pi times alpha minus alpha naught. It was a little bit lower. So people who were building the aircraft, remember 1914 to 1918, there was a First World War going on. People already started using airplanes for military purposes, observation purposes, maybe just to take pictures, reconnaissance, that type of thing. Germans even flew and dropped bombs over England, not during the Second World War, but even during the First World War. But those aircraft were very, very small. They could not carry a lot of weapons, a lot of ammunition, so the damage was minimal. But they noticed both on the Asian, European side, France, Germany, England, but also in the United States side, everybody found my lift is not 2 pi times alpha minus alpha naught in 3D, but something lower. Also, the 3D wing had a drag that's more than the 2D drag polar that we have been computing in our X-file. So they also found if the aspect ratio of the wing is defined as the square of the span of the wing from wingtip to wingtip divided by the projected wing area. So if you project the airplane from the top, take a picture, project to the ground, the area of the wing, including the wing buried inside the airplane, the fuselage, there'll be the wing planform, that's an area. So that goes in the denominator in meters squared. Span is in meters, wingtip to wingtip, so that's also meter squared. So the ratio is a non-dimensional number. Now, commercial aircraft, that ones that they had earlier generation, and gliders had a very, very large aspect ratio, like a 10, 12, something even longer. They had somewhat lower drag, but transport aircraft, the one like we see, Boeing type of things we see today, they are of the aspect ratio 7 to 8. They had a little bit higher drag. Bombers had an even lower aspect ratio because they should be able to maneuver, dodge the bullets. So if they have a large wing, large moment of inertia, it's going to take a long time to turn, roll, turn, and so forth. Just like a big truck takes a large radius of curvature to turn. On the other hand, a tiny bicycle can turn on a dime, right? So on the other hand, fighter aircraft had even smaller aspect ratio, sometimes 3, 4, 5. So the smaller the aspect ratio, the higher the drag. So the industries who are building these aircraft didn't know what was going on. So they came to two people. In Germany, they came to Prandtl. And in England, they came to Lanchester. We know more about Lanchester only because it was written in English, and also because of the war. What was going on in Germany was under wraps, so not too many people knew. Although Prandtl was apolitical, he was a scientist, didn't care about politics one way or the other. He was developing the theory. But he published it later on in 1918 to 1919. He called it a lifting line theory. Then people realized these two folks, Lanchester and Prandtl, have been working together on the same thing, but independent of each other. So sometimes it's called a Lanchester-Prandtl theory or Prandtl theory. Then came Glover, the same guy we saw in the thin airfoil theory. He came up with the Fourier series. Just like in thin airfoil theory, we used a Fourier series to distribute the circulation along a chord line. In the case of a 3D wing, he distributed the circulation from one wingtip to the other wingtip. not in terms of a physical distance, x or y or z, but in terms of some angles, cosine theta, sine theta. We will see that later on. So this theory allowed unswept, that means we cannot sweep it, but the wing can be very general. It could be tapered, be twisted. You could have a different airfoils, different places. It was very easy to work on it. So we will go through the theory today, and you'll be able to work on the homework number 3. And you can bring me questions on homework number 3 to the class on Monday and Wednesday next week. By the next weekend, you'll be submitting it. Okay. So Prandtl came up with a very, very intuitive explanation. So we will turn our attention to what causes this loss of lift and what causes this increase in the drag. So that's the first thing we are going to be looking at. So we are going to look at something called a tip vortices. So when the aircraft is flying, it generates vortices from the wingtip. Now we know that it's caused by the high pressure air from the bottom side flowing around the wingtip from both wingtips, rotating, swirling into a very clearly visible vortex. Sometimes when an airplane is flying overhead, you'll see something called the condensation trail. Where did the condensation trail, what is the word condensation? It comes from the word condense. So inside these vortices, you have a very, very high velocity. Remember gamma over 2 pi r point vortex? So when the velocity goes up at so high, it not only draws its energy from pressure energy, but also internal energy. So the temperature drops. So when the temperature drops, the moisture in the atmosphere condenses. So if you have just enough moisture in the atmosphere, when the planes are flying overhead, sometimes you will see 2 trails, white trails. These are nothing more than a condensed water droplets. When the sunlight hits it, you are able to see it with your naked eye. Okay. So condensation trails were forming. So he said there are some vortices. Okay, well, what do these vortices do? He said these vortices are going to induce a downward directed flow over the wing, which we call a downwash. Okay. This is a picture you could do in a wind tunnel if you have some kind of a sophisticated image velocimetry like the one we have at Georgia Tech. You take a picture of a whole screen, introduce smoke particles and see how fast they travel by taking an image resolution between 2 successive frames. You can process the entire plane, okay, automated. But in the case of Prandtl's time, you have to stick a probe at each and every point, take a data and collect the data. But regardless of how we collect it, we are getting this downward directed velocity, which we call downwash. The farther apart these vortices, larger the aspect ratio, the lower the downwash, at least near the center of the wing, near the fuselage. Of course, when you get closer to the vortex, you'll get a higher velocity. Remember that 1 over 2 pi r, the closer the distance, the higher the velocity. So this is called a downwash. So Prandtl said the free stream is coming along its merry way, but when it sees this downwash over the wing developing, this vector and the downwash vector, which is pointing downward direction, when you combine it, the velocity vector becomes this one. This becomes a new effective velocity vector. So this line where my mouse pointer is the total velocity vector, which is a vector sum of this free stream velocity in the x direction and the vertical downward directed velocity in the z direction. So now lift starts now acting perpendicular to this new direction. So it's actually pointing backwards. So this backward directed lift vector has got one vertical component, which is what is holding up the plane, overcoming the weight. But unfortunately, it's got a horizontal component. So this is called the induced drag. So this is the reason 3-dimensional aircraft have a higher induced drag. The smaller the aspect ratio, stronger the downwash, That means that the longer this vector downward directed as a fraction of this total velocity vector, more the lift vector rotates backwards, longer the induced drag vector, higher the induced drag. So Prandtl and experimentally came up with this kind of a correction factor first. He said this induced drag coefficient, it's just like a lift coefficient is a lift of the airplane, L, divided by 1/2 rho V infinity squared, where V infinity squared is the free stream velocity, times the wing projected area. Once you find the CL, square it, divided by pi, times the aspect ratio, times a factor that depends on the plan form, how the wing is chord is changing, what kind of a aerofoil you are using, how it is twisted, all that good stuff goes in this single factor. But he said this is how the drag can be estimated. So needless to say, gliders had a very, very large aspect ratio, 10 to 12. They had a very low drag. Then current generation transport aircraft will have an aspect ratio of 7 to 8. Only reason you cannot have more than that is you need a real estate between that gate A28 and gate A30 at Delta in Atlanta. If you have a very broad wing, you'll have a problem. So now people are thinking about maybe bending the wingtip and then straightening it out. Others are thinking of also such a large wing, it may bend or twist too much. So thinking of a struts to support it, all kind of a new concepts, which are really redone world concepts from the early 20th century are coming back to increase the aspect ratio. So for bomber wings will have a higher drag, fighter wings will have even higher drag. That's why as soon as an F-18 takes off from a ship deck, he'll get refuel. Then he'll go a couple of 100 miles, then it would need additional fuel. So it needs a lot of logistics support structure to go from point A to point B. Okay. That's because of the excess drag caused by the downwash. So it's a clockwise rotation of the lift vector, which creates a backward directed drag force component in the direction of the flow. So we are going to show this equation analytically. So Prandtl then had to have started modeling it. Of course, Lanchester also started modeling it in England, independent of each other. So at that time, remember we are talking about in 1910, we didn't have CFD. We could not model any of these. Today, in my undergraduate research, I have a 1 credit hour thingy. There are 4 or 5 assignments. One of the assignments is using a software called ANSYS to draw lifting flow over an airfoil. In our Canvas site, I do have some ANSYS resources at the bottom of the course if you want to learn to do how on your own. But this is too far, too much, so he could not do it. Even distributing the circulation over a camber line like Monk did and Glover did was too much. So remember in our homework number 2, we lumped everything at a quarter chord point as a single vortex, which contained the same circulation as the circulation around this camber line in thin aerofoil theory, or the circulation over the complete aerofoil in the panel theory with the boundary layer. So he said, I'm going to lump all of this at the quarter chord point. Okay. So in homework number 2, we just had a 1 aerofoil section, but now we have a wing. So if you think of this direction as a y direction, streamwise direction is x direction. Okay, sorry. So this circulation is going to vary from wingtip to wingtip. That's because right at the wingtip, lift will go to 0 because the bottom pressure and top pressure will become equal because this is the edge. So the high pressure air from the bottom will flow around and then equate to the low pressure air. So we will not have any lift at the wingtip and wingtip. So the gamma is going to completely change from point to point to point. So Prandtl said, if I could somehow solve for this gamma, then I can integrate it and find the lift. In your homework number 2, you solve for this gamma by applying the boundary condition at the 3/4 chord point. Then you found just a two-dimensional lift. Then you found a two-dimensional lift coefficient. Now, Prandtl had to do it in 3 dimensions, except now the problem was a little bit more complicated because this gamma was changing all over the place. It's not just one number. So he said, if I can somehow solve for this gamma, then I can find a lift and I can find a lift coefficient. But there were some objections that were raised. We are going to cover something called Helmholtz theorems. Helmholtz was a scientist. He also lived and died during the 19th century. Prandtl and Lanczos were developing these things in the early part of the 20th century. So Helmholtz was come and gone, he was dead. But his theorem were living on forever. So one of the theorems that said was a vortex strength cannot abruptly increase or decrease in space. There must be some physical mechanism that adds circulation. There must be a physical mechanism for removing circulation. One physical way of looking at it is vortices have fluid particles that are swirling about. They have an angular momentum. If the angular momentum cannot abruptly increase or decrease, just like a linear momentum cannot abruptly increase or decrease, there must be some physical mechanism that causes the change in the angular momentum. Otherwise, angular momentum must be conserved. Okay, just like a linear momentum must be conserved. A body in motion continues to stay in motion, like the Newton's law said. A body in rotation, some of these ice skaters, they keep spinning. If there's no friction, their angular momentum will be conserved forever. They'll be spinning forever, right? So objections were raised to this model, especially abruptly increasing or decreasing the circulation without rhyme or reason. So Prandtl said, I do need an explanation for it. I do need a physical model for this. So the Helmholtz theorem, which I will give you the proof next lecture, it said, this is not good. You cannot be changing the span mesh direction gamma abruptly, not good. So Prandtl said, okay, I'm going to overcome this. I'm going to really physically, introduce some trailing vortices. So not only from the tip I get these vortices, anytime circulation changes from gamma 1 to gamma 2, I'm going to be feeding circulation of strength gamma 2 minus gamma 1. So think of like an electrical current. If I go from 1 ampere to 2 ampere, I have to add 1 ampere current at this junction. So circulation the same way. Anytime circulation changes, you have to either bring in the circulation, right-hand screw rule, or you should be removing the circulation. So here, if you go from a circulation of 3.5 to 3, you are removing 0.5 circulation. It should be removed by these vortices. These vortices are very, very weak. That's why we normally do not see with our naked eye. But sometimes you can see with our naked eye. For example, when the flap is deflected, you'll see vortices coming off it. Okay. So let me show you a physical picture of it. I'm going to go to a browser. And I'm going to search for flap edge vortex. Sometimes you get good ones, sometimes you get bad ones. So I do not know what I'm going to get here. So this is a paper. I don't want it. I want an image. So let me go in here. Flap edge vortex. Can you all see this picture by any chance? Are you able to see this? Can you see, get a show of hands, please?
Yes, we can.
Yeah, great. So notice that you have these two trailing condensation trails. They are occurring there because remember we said when you deflect the flap, you are changing the camber. So where you deflect the flap, abruptly the camber changes, abruptly the circulation changes. Whenever the circulation changes, you are going to have some trailing vortices. They will sometimes form a condensation trail. That's what's happening here. Okay. So you see, this is not tip vortex because the tip vortex will be at the wing tip. Okay. So condensation trail can be seen from the flap edge vortices. Okay. So here again, the same picture is shown down in here. So there's a plenty of visual proof that this should be needed. So Prandtl said, I'm going to generate a whole bunch of straight line vortices, infinitely large number of them. They all either bring in circulation or they are removing circulation. So when they bring in a circulation, right-hand screw rule, when the screwdriver advances towards this line, circulation is going to increase. When the right-hand screw retreats from the lifting line, it's going to remove circulation. So this itself, the quarter chord line, is called the lifting line because that's where we are concentrating all our lift from root to tip, wingtip to wingtip. Then people said, how about these vortices? Where do they end? Prandtl said, easy. That's the starting vortex we talked about earlier. So they have a vortices. So these vortices have a mirror image out here, the starting vortex. If this is a +2, this is going to be -2. If it's going to be +3, it's going to be -3. So just like you have a bound circulation over an aerofoil, opposite circulation over the starting vortex. So everything perfectly cancels. This starting vortex is eventually infinitely far away from the wing. So it does not affect what's going on the wing. But these vortices are very close to the wing, so we need to account for their presence. We have to acknowledge their presence and do something about it. So Prandtl developed a theory for it. We are going to go over it in our lecture. So in summary, at each span station, all the vorticity is lumped into a vortex called a quarter gamma at the quarter chord. So gamma is going to vary along the y direction. Y is the span-wise direction. To the pilot's left will be minus half a semi-span, b over 2. B is the span. To the pilot's right, it will be plus half a semi-span or a plus b over 2. So y will vary from minus b over 2, lowercase b over 2, to plus b over 2. So gamma is going to change along y. So that line is called the lifting line. And the line, of course, in our current theory is unswept. Later on, we're going to include the sweep effect a little bit later. What did we give up? We lumped everything at a quarter chord point so we can get a lift, but we can't get a pitching moment. Just like in homework number 2, you got an expression for CL, but you did not get an expression for CM. Thin aerofoil, because it distributed the lift, it knew how much was generated near the leading edge, how much generated near the trailing edge, so it could compute the pitching moment, but not in this model. So we will have to compute the lift, then look up a table of CL versus CD for viscous drag, CL versus CM pitching moment. For pitching moment, you'll have to do it. But his theory will give you the lift and induced drag. Okay. All right. Now, so we'll have to use a test data to get the pitching moment for a given CL. You know, if somebody gives you a CL, look up the alpha. At that alpha, look up the pitching moment. Okay. So this is what will be done in the practice if we had this lifting line theory, because Prandtl's theory cannot give this number at all. Of course, it cannot also give the drag at all. Okay. So this is the picture Prandtl had. Okay. So there are right-hand screws advancing towards the wing, starting with 0, slowly increase the lift. Then the same right-hand screws advance away from the wing, away from the lifting line, removing the circulation, bringing it back to 0. And this is the starting vortex. So these are called trailing vortices. They are not visible to the naked eye because they are very weak. We usually only see the tip vortex and any flap edge vortex, which is strong enough to be seen with naked eye. So Prandtl said, I need to compute the downwash if I'm going to do the drag or rearward rotation of the lift. So he said, if I have a lifting line, if I pick a point, remember in our homework number 2, we picked the control point at 3/4 chord point. in Prandtl's theory, he said, I'm going to apply the boundary condition directly at the quarter chord point itself. So he applied it at the quarter chord. Okay. It turns out if you do at the 3/4 chord point, you could do a swept wing. If without it, you cannot handle the sweep effects at all. But in those days, First World War aircraft did not have a lot of sweep, so he didn't have to worry about it. He said, I'm going to go ahead and apply my boundary condition here. So if a vortex is separated by a point where I'm computing the induced velocity by some distance, y minus y naught, we don't need to know which is y naught, okay? So the vortex is going to produce a downward directed velocity, this clockwise vortex, at the point P. Now, we can compute the downward directed velocity in 2D pretty easily. It has a gamma over 2 pi r. So if you put a vortex here, if somebody asks you what is the downward directed velocity here, you just say gamma over 2 pi times distance between where the vortex is and where I'm applying my boundary condition. In your homework number 2, you put the vortex at quarter chord point, you applied the boundary condition at 3/4 chord point. Same principle. So this is what happens in 2D. But 2D vortices are infinitely long. So if you think of this as a plane, the vortex comes towards you, coming from my computer screen towards me infinitely, and it also goes into the screen, goes the other way infinitely. So it's an infinitely long vortex. So we think of it as a 2D vortex. It goes from minus infinity to plus infinity. But in the case of a lifting line, it's only half as long. It goes from 0 to infinity. So we have to analytically integrate something called the Biot-Savart law that we alluded to in our last lecture on 3D building blocks from this point all the way to infinity. So if you integrate the Biot-Savart law from x equal to 0, y x equal to 0 to x to infinity, then you get the downward directed velocity from a vortex as half of the 2 pi. This is twice as long. This is half as long. So it turns out the induced velocity is not gamma over 2 pi times distance, but gamma over 4 pi times distance. So he said, if I integrate this, I can get the total downward directed velocity. So he said I can integrate it from wingtip to wingtip. So downward directed velocity, which we call the downwash, at any point y naught on the wing can be integrated to get this expression. There was one big problem. The unknown is we don't know how the circulation is changing along the wing. So this is an integral with an unknown buried inside the integral. So we will end up with an integral equation. Okay. So this is the downward directed velocity. Then Prandtl said, okay, now the downward directed velocity will produce a rotation of the lift V infinity. This is the original V infinity. Now I vectorially added this downward. This is a new V infinity. So this rotation angle, he called it an induced angle of attack. It's an arctan of this downwash divided by V infinity, opposite side by adjacent side. This downwash is usually small, tens of meters per second. Your flight velocity is very high, 50 meters per second, maybe 100 meters per second. Okay. So this is a small number. So arctan of a small number is replaced by that number in radians. So this is an approximation he did. So he said, I can find my lift coefficient as 2 pi or whatever A naught is, lift curve slope is, alpha minus alpha naught, minus this additional reduction in the angle of attack, effective angle of attack. That's why I get a lower lift in 3D. That's why I'm going to get a lower lift for a wing. So he had kind of a physically, intuitively explained the reason we get a lower lift in 3 dimensions is because this downwash reduces the angle of attack. Therefore, each section produces less lift. Therefore, the total wing produces less lift. This A naught could be 2 pi if you don't know the answer. If there's a measured data is available, people will use the lift curve slope at each span location. If you know the airfoil shape, you can test it in a wind tunnel. as a function of alpha, get this lift curve slope. In the absence of such internal data, we will assume 2 pi as long as all these angles are in radians. Now, lift is 1/2 rho velocity squared times cot times the CL. This is just the algebra. Now, lift could be related to circulation. So I can write this W as taking everything to the right-hand side and then taking this alpha and alpha naught to the right-hand side. Then I can write an expression that is given, something like this here. All right. So this is one expression for W. And then here we had another expression for W. So if we equate this expression for W with this expression for W, you get a very, very complicated, long expression like this. In our homework, we're going to use a Glavert methodology where he used a series substitution and then he integrated this. Hopefully, I'll be able to complete enough of it so you can get started. But Glavert solved this numerically. But in Prandtl's days, that was not there yet when he was developing this theory and also in Lanchester. So Prandtl said, I'm going to assume a solution for gamma and see what happens. Okay, that's the best I could do. I'm going to assume a functional form of gamma, and I'm going to put it in this integral, integrate it, solve for the alpha, solve for the W, solve for the loss of lift. By the way, if I know this angle, I know my rearward rotation of the lift vector. So if I know my lift vector, rearward rotation, L prime times sine of this alpha will be my drag. So I can also get the induced drag. So he said, I'm going to analytically assume a solution and see what happens. So drag is, if I know this angle somehow, I know it is the same angle here. So the lift is here. Lift time, this vertical thing is lift. This is the total lift here. So this angle is lift times, you could think of it as a sine of alpha, which is tan of alpha, which is W over V infinity. Again, sine of alpha equal to tan of alpha equal to alpha when alpha is small. So this induced angle of attack is of the order of a few degrees, 1 or 2 degrees in practice. Therefore, he could justify small angle assumptions. So Prandtl said, I'm going to assume a elliptically loaded wing. What do we mean by elliptically loaded wing? This function of gamma varies from wingtip. This wingtip is called y equal to plus b over 2 to the pilot's right. On the other side of the y-axis here, you have a minus y over b over 2. So from minus b over 2 to plus b over 2, if I draw this curve, it looks like a half an ellipse. This is the minor axis. This is the major axis. So y divided by b over major axis squared, semi-major axis squared, plus this vertical distance divided by semi-minor axis squared equal to 1 is an equation of an ellipse. So he assumed, I'm going to assume an elliptically loaded wing. It turns out this produces the lowest induced drag. That's why it's of particular significance. So he said, I'm going to assume a functional form. I'm going to plug it in here and see what happens. As soon as he did that, he had all kind of a complication. It was hard to integrate this integral, hard to solve this analytically. So even Prandtl knew I had to do some kind of a change of variable. You remember in Calc 1, if somebody gives you an integral, if you can't integrate it, you change the variable and see whether you could do something better. So that's what Prandtl also did. So he assumed that this y varies as a minus of semi-span. B is the span. B over 2 is half the span, called semi-span, cosine of theta. That means to the left side, theta is 0. To the right side, theta equal to pi. Cosine of pi is cosine of 180 degrees is minus 1. So minus of minus 1 becomes plus 1. Okay, so the right side of the pilot is plus b over 2. Left side is minus b over 2. So the angle varies from 0 to 180 degrees, 0 to pi. The point where we are computing the downwards, point P, you use the same relationship. So if you assume this y if you plug it into this equation, y equal to b over 2 times cosine theta, this becomes cosine squared theta. You can bring it to the right side. 1 minus cosine squared theta is sine squared theta. If you take now the square root, gamma becomes equal to gamma max times sine theta. Then you can find the differential of gamma as gamma max times cosine theta d theta. So by the way, this is the first term in a Fourier series. Glavert is going to produce a long series, infinitely long series. In your homework, you'll be taking the first couple of terms and then solving for it by hand. Okay. In my MATLAB code, I'll take 10 to 20 terms and show you how to solve it on the computer. Okay. All right. So I hope you are able to follow this along. So he put this d gamma, gamma, all of these things in here, and he replaced y equal to minus b over 2 cosine theta, minus b over 2 cosine theta naught. Integral went from 0 to pi, so he analytically integrated it. So there were lots of nice tables of integral, so he could integrate it analytically. So it gave him the analytical expression for this downwash as the maximum value of gamma at the middle of the wing, which is this peak value, divided by 2 times the span of the wing. So the larger the span, lower the downwash. He had to take advantage of a table of integrals relationship. In your homework number 3, you would not need any table of integrals. It's all been worked out in the theory, so it's purely a numerical problem. So for him, an elliptically loaded wing, this downward directed velocity downwash is going to be a uniform downwash. Theoretically, it turns out this is the best. As a result of it, you're going to get the lowest induced drag. If you have a non-uniform bumpy downwash, then you're always going to get a higher drag. Okay? So downwash is a constant. Theoretically, it turns out to be the best from an induced drag perspective. How about lift? I'm going to integrate it, he said, my gamma y. So plug in for the gamma, this relationship. Plug in for dy, minus b over 2 cosine theta. If you do it, sine theta d theta with a minus will go away. Plug it in. Then you get for the lift, basically this number. So the maximum circulation could be found in terms of a lift. Why do I need the maximum circulation in terms of the lift? Because then I can find my downwash. Why prefer lift? Because lift equal to weight of the aircraft. So all these properties are known. So we can find the maximum circulation. We can find the downwash. So once you have the downwash, you can solve for the drag coefficient as find the gamma max, find the downwash, then find the angle of induced angle of attack. These are some intermediate expressions. Then his drag became the rearward tilt of the lift. So lift times alpha I dy. Lift is rho v infinity gamma. I know I'm throwing a lot of equations at you. Rho v infinity gamma dy. Downwash is known. So he integrated for this simple wing, elliptically loaded wing. He was able to analytically integrate everything. So he got this as the induced drag. So this is the lowest possible induced drag for a given lift coefficient. So designers, if you work for Gulfstream or Boeing or Airbus or Embraer or a Chinese aircraft or a Indian Airlines, Air India, Hindustan Aeronautics, they're going to ask you to come up with the lowest possible induced drag. Of course, you're limited also by the aspect ratio. So you can twist the wing, taper the wing, try to come up with an elliptically loaded wing. That's the goal. Okay, now for the elliptically loaded wing, if you have same airfoil, same alpha, or an untwisted wing, okay? So alpha is just a constant value. It's not changing from root to tip. same airfoil, so same lift curve slope, same angle of zero lift. Then this part could be, when we integrate it, all these constants will come out of the picture. Then the chord, when you integrate chord versus dy, it's just a projected area of the wing, which is the wing area. So for a elliptically loaded wing with untwisted, with the same aerofoils, then you get a lift as this. He was trying to get an estimate for the lift curve slope. Okay. So he said, if this is my lift, now my alpha is from an elliptically loaded wing is this number from the previous set of equations. Put it in there. You bring it to the left-hand side, group all the CL terms. Then if you do dCl d alpha, three-dimensional lift curve slope, it's not 2 pi, it's not a test data from a aerofoil test, it's 2 pi divided by some factor that's greater than 1. This is why the 3D wings have a lower lift curve slope than 2D aerofoils. Therefore, the 3D wings are going to produce less lift. The smaller the aspect ratio, the bigger this number, bigger the denominator, lower the lift curve slope, lower the lift. So Prandtl was able to explain all of this for his elliptically loaded wing. Then came Glavert. Okay, so Glavert said, I'm going to assume non-uniform, not an elliptically loaded wing, but a general wing. So, this I will go over it again on Monday one more time, this part. But today I'm skipping this one about the MATLAB code part of it. But Glavert is going to do a different way than Prandtl did for a more general lift distribution, not just a pure ellipse. So everything has to be a little bit more complicated. So he used the same transformation like Prandtl did. Again, it goes from, integral goes from 0 to pi. But rather than assuming an elliptically loaded wing, which produced gamma equal to gamma max times sine of theta, just a one term in the Fourier series, he assumed an infinite series, okay? Again, we are going to stop it with just the first two terms in our homework number 3, A1 and A3, truncated. But you can keep more terms, but it turns out you have to keep only the odd terms, not even terms. Also, you should not have a cosine n theta. In the classroom on Monday, I will explain if we keep even terms, sine of 2 theta, sine of 2 theta, sine of 3 theta, etc. Because the theta is going from 0 to pi, on one side you'll get a positive wing, other side you'll get a negative wing, then you'll get an unbalanced rolling moment. So for a symmetrically left and right, steady level flight, we cannot have an even term, sine of 2 theta, sine of 4 theta, sine of 6 theta. They will produce unevenly balanced lift. Okay, so that's why we do not keep the even terms. Also, we do not add a cosine n theta terms like we do in a normal Fourier series, because when theta goes to 0, cosine of n theta is +1 or -1. So you get a finite lift at the wingtip, theta or pi. We know that we cannot have any lift. This guarantees when theta equal to 0 or theta equal to pi, circulation is 0. So that's why we keep only sine terms, and we only keep odd terms so that the left and right side of the wing produce the same lift. Then he was able to take a differential of it, so put this y naught and y, change a variable like Prandtl did. So now he got a series expression. Each and every term in the series had to be divided by this number. Okay. So b canceled out. Okay, you still had a v infinity, hanging around somewhere here. Okay, and you got some expression. Remember, circulation is a distance times velocity. So we bring in the distance unit, the velocity unit. So these coefficients are non-dimensional numbers. So all of these are non-dimensional. Dimensionality is buried in here in the coefficients that are up here. Now, integrating for the W, take this expression, throw it in here, integrate it. You get a bunch of integrations, each and every term. but they could be integrated using table of integrals. So you get this expression for number. Prandtl just had one term, so he just had a sine n theta by sine theta, sine 1 theta by sine theta. So this became 1. So alpha I was just one constant. Whereas for a general wing, it's going to vary, alpha I is going to vary all over the span, depending on where this theta is located. But theta is a function of where you're computing it, which is the y. Okay. So Glover's is a more general expression. Again, in our homework, we're going to do A1 and A3. Okay. And now, throw all of these things in here, analytically integrated. Now we get a linear equation for A1, A3, A5, A7, and so forth. In our homework, you will do for just 2 terms. My MATLAB code you can keep 10 terms, 20 terms. You just change a number, then you can solve for it. Okay. But how do I solve it? Then how do I get lift? How do I get the drag? That's the important question, right? So after you solve for A1, A3, A5, etc., I'm going to do a worked out example in a minute. I may not be able to complete it, but you'll be able to look at it and follow your homework in that process. So once you have the gamma this way, all you have to do is rho v infinity gamma is L prime. So rho v infinity gamma integrate with respect to dy. Remember, y is minus b over 2 cosine theta. So dy is plus b over 2 sine theta d theta. So plug it in here and then integrate for the lift. Only you'll get a sine, only the first term will contribute. Sine theta times d theta. All the other terms, sine of 2 theta times sine of theta, sine of 3 theta times sine of theta, because of the orthogonal nature of the functions, they'll all go to 0. So you get a lift value just from the first term. Again, you can find other terms and find a downwash. Then once you have the downwash, if you take the lift multiplied by the downwash and integrate it, you'll get a drag. Remember the rearward tilt of the lift times sine of alpha, which is this number. So lift includes gamma, circulation. W is a function of circulation. So multiply them and take an integral. After some algebra, you get an expression like this, where the leading term is Prandtl's lifting length, elliptically loaded wing. That's the lowest possible drag. If you have any other wing, you get extra drag. That's why we say that elliptically loaded wing is the ideal wing. Practical wings will have a slightly non-zero A3, A5, etc. So you need to find A3, A1 to correct for it. In your homework, you're going to keep just 2 terms, A1 and A3. So you'll find this extra term. We are neglecting A5, A7, etc. In my computer code, you can keep 10 terms, 20 terms if you like. All right. Now, very quickly, I have a worked out example here. Our homework problem is very similar to it. If you think of the span as a B, if the chord is C, rectangular wing in our homework, so aspect ratio is very easy, right? B squared is the span squared. Wing area is B times C. Therefore, the span divided by the chord is the homework quiz one. You can handwrite it. You don't need to type it. So you can find the wing geometry. Assume lift curve slope. Our homework number 3, the zero lift angle is 0 because we're using symmetric angle of attack. So alpha is 4. So if you follow this example, you'll be able to get started on the homework number 3 this weekend. Then Monday, when I explain some more details, it'll become more clear to you. So how do I solve this problem? I'm going to solve this equation. So I'm going to keep 2 terms, A1 and A3. So remember, all of these came by integration, right? So when you do integration, you would have studied something called the trapezoidal rule, where you find the integrand in the middle of a segment and integrate it. So the wing goes from minus pi over b over 2 to plus b over 2. So it's minus pi to plus pi. So in the middle of the wing is pi over 2, right where the pilot is sitting. So we take 1/2 of the wing. So we're going from 0 to 90 degrees. So apply this equation at 45 degrees and at 90 degrees. Equal spacing gives you the best answers, the most accurate answers. So don't be randomly choosing 60 degrees and 85 degrees or so. You'll still get two equations, but in practice that provides very, very poor answers. So the left side, this is 4 degrees. Alpha naught is 1.2 degrees, so it's 5.2 degrees. Immediately convert that into radians. Okay. Then B over C for a rectangular wing is the aspect ratio. Here you know B, but you need to know the chord at that particular location corresponding to 45 degrees or 90 degrees. I'm going to show you how to do that. As soon as you know this coefficient, you can apply theta equal to 45 degrees or 90 degrees, expand this series. If you keep 2 terms, you'll get 2 terms from here, 2 terms here. So apply this equation once at 90 degrees, once at 45 degrees, you get a 2x2 system of equation for A1 and A3. That's exactly what you're going to be doing in your homework number 3. So how do I do it? At theta equal to 90 degrees, y naught is 0. That means I'm right at the center of the wing. So I'm already given the root chord. So that's what I will be using here, root chord. I'll use the span. But when I do that theta naught equal to 45 degrees, I'm not at the root chord. I'm somewhere between the wingtip and somewhere near the root. So if you have a linearly tapered wing, if you know the root chord, if you know the tip chord, if you know the semi-span distance, you can estimate how is the chord decreasing as I go from root to the tip. Then the farther out you go, the smaller the chord, you can compute the local chord. So for a linearly tapered wing called trapezoidal wing, we can solve it. Okay. So once we have it, you will get an expression for C. So that's what we would do at a 45-degree angle here. So we will apply this equation twice, once at 90 degrees, once at 45 degrees, also in your homework number 3. In your homework number 3, chord is a constant, span is a constant, so this part is a constant. A naught is 2 pi. So now let's write the 2x2 system of equations. Sine of 90 degrees is 1. Sine of 3 times 90 degrees is minus 1. Sine of 45 degrees by sine of 45 degrees is 1. Sine of 135 degrees by sine of 45 degrees is minus, n is 3a3, okay? So you will get expressions like that, okay? So you will get equations of this nature. Now, at the 135 by 45 is plus. 270 by 90, you get a minus here. Okay, so you get a 2x2 system of equation. Solve for A1, A3. Plug it in here to get the lift. Plug it in here to get the drag. So in your homework, I'm going to stop in a minute. You're doing a problem very similar to this, except there's no taper. So the chord is a constant, span is a constant. And you can solve this problem with a very, very similar approach. It's a symmetric aerofoil, so 0 lift angle is 0. I've given you the alpha, so you can solve for the CL at 4 degrees. Then CL at 0 degrees is 0, right? Because it's a symmetric, untwisted wing in my homework. So lift curve slope is delta CL by delta alpha. That is CL at 4 degrees divided by 4 degrees in radians. That gives you the lift curve slope. So in my homework, I'm asking you to find the lift curve slope. So once you know the CL at 4 degrees, you should be able to solve for it. So I'm going to stop here today, and I'm going to revisit this material on Monday class, and then cover some more material. but you have enough information in your hand to get started on the homework number 3. Okay, please get started on it so you can finish it maybe this weekend or by Monday. Then you have all of next week and the following week to get ready for the exam, which is on the 26th. Okay, remember today is already the I've forgotten what day today is, but you know, we have the 11th. So 15 days from now, you have your first quiz. So you want to get the homework away from you, finish it. By the way, you can check your answers with my MATLAB code. I'll also show you how to do it Monday. Okay. So let's stop here. Thank you all for attending. There was one question. Somebody asked to do a handwrite exam or type it. Handwritten is fine. Then you can scan it. You don't need to type anything in the quiz. Thank you.
Professor,
Yes.
I have
Yeah.
one question.
Could you speak louder, please?
Can you hear me?
Yeah.
Can you please go back to slide 23?
Okay. Let's see.
It's very mathematical. I just didn't understand. So in here, when we are computing the downwash, we have y naught minus y, but in the further calculations, when we do it, it's changed to y minus y naught. So is there any reason why we are doing this, or
Yeah, you know, you could take the vortex as y naught and the control point as y, or you can take a vortex as y and the control point as y naught. Okay, it's just the distance between the two. Okay.
oh,
Yeah. So if I express gamma as a function of y naught,
okay.
then my control point will have a y. Okay, then the integral will go from y naught from minus b over 2 to plus b over 2. Very good catch, Shahat, but it doesn't matter as long as you call one as a variable, running variable that you integrate over. Other one is a fixed point.
Okay.
All right.
Sure.
Yeah. Thank you.
Thank you.
Any other questions? Let me look at the chat box to see if there are any other questions asked here. I don't see any other question.
Good morning, Professor. I have a
Yes.
couple questions.
Mhm.
So first off, previously we said that there is circulation up on the top surface of the airfoil and on the bottom surface,
Right,
with both being in opposite directions.
right.
And we concluded that the net circulation of the entire airfoil goes clockwise because
Mhm.
the top surface circulation is stronger than the bottom.
Yeah. Mhm.
Can I know why is the top circulation stronger than the bottom?
Okay, remember that circulation produces the velocity distribution.
Mm-hmm.
The velocity distribution produces the pressure change. So on the top surface, you want to have a lower pressure. So we want to add to the free stream velocity.
Mm-hmm.
Remember, clockwise vortex will produces a left to right velocity on the top, right to left velocity on the bottom. Okay.
Yes.
With the lifting cylinder, if you spin it clockwise, it's going to produce a lift upwards, counterclockwise downward. So by hook or crook, by either changing the angle of attack or by changing the camber, we should somehow achieve higher clockwise vorticity on the top than the bottom to produce lift. Otherwise, produce a downward directed lift. Yeah.
Right. Okay. So to like summarize all of that, it's mostly because since at the top there is lower pressure, meaning higher velocity, hence higher circulation, hence the net circulation is clockwise on the entire airfoil.
Correct. Yeah. Pressure difference is the result. The cause is the clockwise vorticity.
Got it.
Yeah. So we cannot say the pressure causes the vortex to spin clockwise. We should say the vortex spins clockwise. That produces this pressure distribution. Yeah.
Okay, perfect.
Good. Mm-hmm.
And then one other question is that between a doublet and a vortex, so I understand that a doublet is a source plus a sink. So basically flow is going
each other. Yeah. Yeah.
Yeah. So basically the flow is going from the source to the sink and then from the sink back to, oh, it doesn't go back. Okay.
Yeah. But also it may that flow direction may go a long distance before it gets sucked into the sink. Okay, that's what produces this number 8 shaped velocity distribution. That's why we call it a doublet. If you think of an 8, the number 8 has got a circle on the top, circle on the bottom.
Yes.
So the source will produce a mass that goes over a circle and comes back to the sink. Not necessarily directly, although they could directly go along the x-axis, but the other particles will go around the circle and come back to the sink.
Okay,
Yeah.
got it.
Yeah.
Awesome. Yeah, I think that's it. Thank you so much.
Already. And the doublet by itself, at least in 2D, cannot produce any lift.
Yeah.
The top, it's going from this way, clockwise circulation, and the bottom, it's going in the same direction. So when you do a line integral, top and bottom will cancel.
Cancel out.
Yeah.
Okay.
Yeah. Thank you.
Perfect. Thank you.
Good. Thank you. Are there any other questions? Okay, I'm going to stop sharing, and I'll also leave at this point. Thank you all for joining.